Every second, somewhere in the cosmos, a galaxy crosses an invisible line and vanishes from our future forever. Light from over 2 trillion galaxies races toward Earth, but most of that light will never arrive. We stand inside a sphere that stretches nearly 62 billion light-years in every direction, surrounded by an edge we can see forming in real time. Beyond that boundary lies infinity itself, endless and unknowable. You're about to discover how the universe can be limitless and still have walls, how space expands faster than light allows, and why everything we can ever see is just the tiniest fraction of what exists. If this journey through cosmic paradoxes grabs you, hit that like button and subscribe. Prepare yourselves. We begin. Something impossible is happening right in front of you. The universe stretches forever in every direction, endless and without boundaries. Yet you stand at the center of a sphere that has edges you can measure precisely. Both statements are true. Both seem to contradict each other. Welcome to the single most mind-bending paradox in cosmology, where infinity itself comes with limits. Think about this carefully. If you ask whether the cosmos has an edge, the answer is no. Space continues outward without walls, without borders, without any kind of cosmic fence marking where reality ends. Galaxies exist beyond galaxies, structures beyond structures, extending into distances so vast that numbers become meaningless. The universe confirmed through countless observations is likely infinite in extent, but here comes the twist that changes everything. You cannot see all of it. You cannot reach all of it. You cannot even receive light from all of it. Despite living in an infinite cosmos, you are trapped inside a bubble. This bubble has measurable boundaries, real limits, and those limits are closing in on you right now. The edge isn't made of matter or energy. Nothing physical blocks your view. Instead, the boundary emerges from something far stranger. Time itself creates your prison. Light travels at exactly one speed through empty space, roughly 186,000 miles per second. Nothing moves faster. This cosmic speed limit has been the same since the universe began, roughly 13.8 billion years ago. Now, combine these two facts and you hit a wall. Light from distant regions has been racing toward Earth since the beginning of time, but it hasn't arrived yet. Some light will reach us tomorrow. Some will arrive in a billion years, but vast stretches of space sit so far away that their light will never complete the journey. That unreachable distance defines your edge. Scientists call this boundary the cosmic horizon, and it surrounds you in all directions. Everything inside this sphere represents the observable universe, the only region you can possibly detect or interact with. Everything beyond remains forever hidden, separated not by distance alone, but by the structure of spacetime itself. You could build a spacecraft capable of traveling at light speed, point it toward that horizon, and accelerate for eternity. You would never reach it. The boundary would move away faster than you could approach. This gets stranger still. Your horizon is not the same as someone else's horizon. An observer on a planet in the Andromeda galaxy sees a different sphere, centered on their location. Parts of their observable universe overlap with yours, but vast regions they can see remain invisible to you. Every point in space has its own cosmic horizon, its own bubble, its own edge. Infinity contains countless edges, each one real, each one unique. We live in a universe that is both boundless and bounded, eternal and limited, infinite and trapped. But the details of this paradox reveal something even more unsettling about the nature of reality itself. You are the exact center of the observable universe. Stand anywhere on Earth, anywhere in the galaxy, anywhere in the cosmos, and the same rule applies. You occupy the middle of a sphere that extends equally in all directions. Move one step to the left, and your sphere moves with you. Travel 1,000,000 light-years and nothing changes. The bubble follows you perfectly, always centered, always the same size. This isn't an illusion or a trick of perspective. This is fundamental cosmic geometry. Picture yourself standing in an enormous dark warehouse with a single flashlight. The beam illuminates a circle around you, creating a boundary between what you can see and what remains in darkness. Walk forward and the circle moves. The lit area never changes shape or size, but different parts of the warehouse come into view while others fade behind you. Your cosmic horizon works exactly this way, except the flashlight is time itself and the warehouse is infinite. Every observer in the universe experiences this same phenomenon. An alien civilization 3 billion light-years away sees their own sphere, their own horizon, their own observable universe. Some of the galaxies they can detect exist beyond your reach, invisible to you forever. Meanwhile, you can see galaxies that remain eternally hidden from them. The cosmos reveals itself differently to every observer, granting each one a unique window into infinity. This creates a staggering realization. No observer can see the entire universe. No location offers a complete view. Even if you could somehow survey every galaxy in your observable region, catalog every star, map every structure, you would still have examined only a tiny fraction of what exists. The full universe extends far beyond what any single observer can detect. Infinity ensures that everyone sees merely a sample, a cosmic preview, never the whole show. But here comes something that makes this even stranger. Your observable universe is not just large. The sphere surrounding you measures roughly 92 billion light-years across. That distance contains approximately 2 trillion galaxies, each holding hundreds of billions of stars. The numbers become incomprehensible quickly, yet this entire region, this vast cosmic domain, represents only a minuscule portion of total existence. If the universe is truly infinite, then your observable sphere is infinitely smaller than the whole, 0% of infinity. Your bubble contains everything you can ever see, measure, or interact with. Every photon that strikes your eye or your telescope comes from within this sphere. Every scientific discovery, every astronomical observation, every piece of data about the cosmos originates from inside these boundaries. You are cosmically isolated, separated from the rest of infinity by unbreachable limits. What determines the size of your bubble lies at the heart of the paradox itself. Light lies to you constantly about distance. Look at a galaxy 13 billion light-years away, and you see light that left 13 billion years ago. Simple math suggests that galaxy sat 13 billion light-years from Earth when it released those photons. Wrong. The galaxy was actually much closer when the light began its journey. By the time those photons reach your telescope, that same galaxy now sits far beyond 13 billion light-years. The light traveled through expanding space, and space itself betrayed the measurement. This deception reveals something profound about cosmic distance. When astronomers report distances to far objects, they often use light travel time. They measure how long light spent crossing space. A galaxy whose light took 10 billion years to arrive gets labeled as 10 billion light-years away. But that number only tells you when the light left, not where the galaxy sits now. Space expanded during the journey. The galaxy drifted farther away while its light approached you. The current distance exceeds the light travel distance by enormous amounts. Consider the most distant galaxies visible today. Their light has been traveling for over 13 billion years, almost the entire age of the universe. Simple calculation suggests they sit roughly 13 billion light-years away. Reality tells a different story. Those galaxies currently sit more than 46 billion light-years from Earth. The expansion of space during the light's journey stretched the distance by more than 3 times. The galaxies moved while their light was in transit. Now imagine trying to reach one of those galaxies. You build a spacecraft capable of traveling at light speed. You point it toward a galaxy whose light took 12 billion years to reach Earth. You might think the journey would take 12 billion years. You would be catastrophically wrong. That galaxy has been receding the entire time its light traveled toward you. The current distance exceeds 30 billion light-years. Even moving at light speed, you could never catch it. The space between you and that galaxy expands faster than you can close the gap. Distance becomes slippery in an expanding universe. Two galaxies can sit far enough apart that space between them expands faster than light travels. They drift apart at speeds exceeding the cosmic speed limit. Yet neither galaxy moves through space faster than light. They remain stationary in their local space. The space itself stretches, carrying them apart. The expansion of the universe does not obey the same rules as motion through space. This creates regions you can see but never reach. Galaxies beyond a certain distance, currently about 16 billion light-years away, are crossing an invisible threshold. Light leaving them today will never arrive at Earth. The space between us and them expands too quickly. Those galaxies can still send signals to us from their past, but their present and future remain forever disconnected from ours. We can watch their history unfold, but we will never witness what happens to them after a certain point. The cosmos splits into regions separated not by distance but by reachability, and this division reveals the two most important boundaries in the universe. Space itself is growing larger every second. Forget the image of galaxies flying through empty void like bullets through air. That picture misleads you completely. Galaxies mostly stay in place. The space between them expands, creating new distance where none existed before. Imagine a loaf of bread dough with raisins mixed throughout. As the dough rises, the raisins move apart, but each raisin remains stationary relative to the dough around it. The dough itself grows, carrying the raisins along. The universe behaves like that dough, except the dough is space-time itself. This expansion has no center and no edge. Every point in space expands equally. An observer in any galaxy would see all other galaxies receding, creating the illusion they occupy the center of expansion. But no true center exists. The universe expands everywhere simultaneously, stretching the fabric of space-time uniformly in all directions. Space does not expand into anything. There is no outside container. The universe is all there is. Measuring this expansion reveals something unexpected. Nearby galaxies recede slowly. Distant galaxies recede faster. Double the distance, and you double the recession speed. A galaxy 1 million light-years away might be drifting from us at 14 miles per second. A galaxy 2 million light-years away drifts at 28 miles per second. This relationship holds across the observable universe. The farther away something sits, the faster it recedes. Now push this pattern to its limit. At some distance, galaxies recede at exactly the speed of light. This distance currently measures about 14 billion light-years. Beyond that boundary, galaxies recede even faster. Some race away at twice light speed, others at 10 times. The most distant observable galaxies recede at roughly 3 times the speed of light. They violate no physical laws because they are not moving through space. Space itself carries them. This creates bizarre consequences. Light from these ultra-distant galaxies travels toward Earth at light speed, the fastest anything can move. Yet the galaxies themselves race away faster than light. The photons make progress toward us, but they fight against an expanding river of space. Imagine swimming upstream in a current flowing faster than you can swim. You move forward through the water, but the water carries you backward faster. You make negative progress toward shore. Light from distant galaxies experiences exactly this. Photons from a galaxy receding at twice light speed travel toward us at light speed, but space expansion carries them backward at twice light speed. Net result is they actually move away from us at light speed. The light loses ground despite traveling at maximum velocity. But here comes the strange part. Early in cosmic history, the expansion rate was slower. Back then, even though that galaxy receded faster than light, its light could make forward progress. The photons gradually closed the distance. Eventually, they entered regions where expansion had slowed enough for them to reach us. We can see galaxies that always receded faster than light. Their light reached us anyway by starting the journey when expansion was slower and gradually entering regions where they could make progress. The observable universe contains countless galaxies that never, at any point in their history, receded slower than light relative to us, yet we can see them clearly. The rules governing cosmic visibility defy simple intuition, but they also define the ultimate boundaries of observation. The sphere surrounding you measures 92 billion light-years across. That boundary marks the farthest distance from which light could have possibly reached Earth since the universe began. Anything beyond that distance remains invisible, not because instruments lack power, but because not enough time has passed for light to complete the journey. The universe is 13.8 billion years old. Light, traveling at constant speed for that entire duration, covers a certain distance. But space expanded while the light traveled, stretching the journey and placing the source much farther away than 13.8 billion light-years. Current calculations place your horizon at 46 billion light-years in every direction. Double that distance and you get the diameter, 92 billion light-years from edge to edge. This sphere contains everything you can possibly observe. Every photon ever detected by human instruments originated from inside this boundary. Every star, every galaxy, every quasar, every cosmic structure visible to telescopes sits within this cosmic prison. Beyond the wall lies infinity, forever inaccessible. But the wall itself appears differently depending on what you look for. The oldest light you can detect is not visible light at all. It comes as microwaves, ancient radiation stretched by expansion into long wavelengths. This radiation fills the entire sky, coming from all directions equally. It represents light released when the universe was just 380,000 years old, about 46 billion light-years away from us today. That shell of ancient light marks the practical edge of observation. Beyond that shell, the universe was opaque. You cannot see farther because light could not travel freely through the early cosmos. Matter was too hot, too dense, too ionized. Photons scattered constantly off free electrons, unable to travel in straight lines. Only after the universe cooled enough for atoms to form did light finally break free. That moment of liberation created the shell of radiation you detect today. Anything that happened before that moment remains hidden behind an impenetrable curtain. This creates a nested set of boundaries. The theoretical limit at 46 billion light-years represents how far light could travel in principle. The practical limit sits at roughly the same distance, but represents the moment the universe became transparent. Between you and that wall lie all 2 trillion galaxies of the observable universe, arranged in an intricate cosmic web of filaments and voids. Beyond the wall lies the unobservable universe, potentially infinite in extent. But even within your sphere, not everything remains reachable. A second boundary exists much closer than the first, currently sitting at about 16 billion light-years away. This boundary separates regions you can see from regions you can influence. Galaxies beyond this closer boundary are crossing a threshold. Even if you sent a light-speed signal toward them right now, that signal would never arrive. Space expands too quickly. The message would drift farther from its target forever, making progress through space but losing ground to expansion. You can see these galaxies, but you can never contact them. They exist in your observable universe but outside your reachable universe. You can watch their past unfold, study their properties, measure their light, but you cannot send them information. You cannot visit them, you cannot interact with them in any way. They are observationally present but causally disconnected, visible ghosts beyond the point of contact. This second boundary shrinks with every passing moment. More galaxies cross it constantly, slipping beyond reach forever. Galaxies at the edge of the observable universe recede at 3.3 times the speed of light. Let that sink in for a moment. The speed of light represents the ultimate cosmic speed limit. Nothing can travel faster, yet galaxies routinely exceed this limit by factors of 2, 3, or more. They violate no laws of physics. They break no rules. The cosmos allows this because the rule about light speed applies to motion through space. not to the expansion of space itself. Special relativity sets the speed limit for objects moving through spacetime. A rocket cannot accelerate to light speed. A particle cannot outrace photons. All motion through space obeys this absolute restriction. But the expansion of the universe involves something different. Space itself grows larger, and that growth has no speed limit. The fabric of space-time can stretch as fast as conditions allow. Distant galaxies carried along by this expansion can recede from each other at any speed whatsoever. Picture two galaxies separated by enormous distance. The space between them expands everywhere simultaneously. Near Earth, a small amount of new space appears every second. Near the distant galaxy, another small amount appears. All along the path connecting them, space expands at the same rate. Add up all these small expansions across millions or billions of light years, and the total distance grows faster than light can travel. Neither galaxy moves through space faster than light, but the space carrying them expands without limit. This creates a strange consequence for light traveling between them. Photons from ultra-distant galaxies fight against expansion. They race toward Earth at maximum speed, but space carries them backward faster than they advance forward. Early in the universe's history, when expansion was slower, these photons could make progress. They gradually closed the distance despite swimming upstream against expansion. Eventually, they entered regions where local expansion had slowed enough for them to reach us. We see them now as ancient, red-shifted light from near the cosmic horizon. But photons emitted from those same galaxies today will never arrive. The current expansion rate exceeds the rate when that ancient light was emitted. Modern photons face a stronger current. They cannot make progress against it. They will drift away from Earth forever, despite traveling at light speed toward us. The galaxy that emitted them recedes faster than its own light can approach us. This defines the event horizon, the boundary separating galaxies we can still communicate with from galaxies forever beyond reach. Every second, about 20,000 galaxies cross this threshold. They slip beyond the event horizon, entering the unreachable realm. You can still see them because their old light continues arriving. But light they emit today, tomorrow, or any time in the future will never complete the journey. You are watching the last visible moments of these galaxies, frozen in time as they cross into cosmic isolation. Over billions of years, they will fade from view completely as their final photons arrive and no new ones follow. The event horizon currently sits about 16 billion light-years away. That makes it much closer than the observable horizon at 46 billion light-years. You can see galaxies far beyond the event horizon because their past light made the journey when conditions were different. But those distant galaxies are already unreachable. They crossed the event horizon long ago. Their current state, their present condition, their modern evolution remain forever hidden from view. This split between observation and interaction defines your cosmic reality. The universe you can see extends much farther than the universe you can reach. 380,000 years after the universe began, something changed forever. Before that moment, the cosmos was a roiling furnace of naked particles. Electrons drifted free, unbound to atomic nuclei. Photons scattered constantly off these free electrons, bouncing from particle to particle like pinballs in a machine. Light could not travel in straight lines. The universe was opaque, a thick plasma fog impenetrable to electromagnetic radiation. You could not see through it any more than you could see through a wall of solid metal. Temperature determined everything. When matter exceeds roughly 5,000 degrees, electrons tear free from atoms. The electromagnetic force binding them breaks down. Protons and electrons drift separately, creating a plasma where charged particles swarm everywhere. Light interacts strongly with free electrons, constantly scattering and redirecting. This creates opacity. Lower the temperature below 5,000 degrees, and electrons recombine with nuclei. Atoms form. Free electrons disappear. Suddenly, light can travel unimpeded across cosmic distances. This transition happened across the entire universe almost simultaneously. As expansion cooled the cosmos, conditions reached the critical temperature. Electrons combined with protons and helium nuclei. Within about 100,000 years, the universe transformed from opaque to transparent. All the light that had been trapped, scattered endlessly by free electrons, suddenly broke free. It streamed outward in every direction, carrying information about the conditions at that moment. That light has been traveling toward you ever since. Stretched by expansion, redshifted from visible light into microwaves, it fills the sky today as a faint glow called the cosmic microwave background. Every direction you look, you detect this ancient radiation. It represents light released from a spherical shell surrounding you, currently sitting about 46 billion light-years away. That shell marks the surface of last scattering, the moment when photons last interacted with matter before beginning their long journey to Earth. This shell is the farthest thing you can see with light. Beyond it, the universe was opaque. Light could not travel freely. You might imagine looking farther back with powerful enough telescopes, but no telescope can pierce the plasma curtain. It represents an absolute barrier to electromagnetic observation. Everything that happened before atoms formed remains hidden behind this wall of scattered light. The first 380,000 years of cosmic history are fundamentally invisible to light-based telescopes. But the cosmic microwave background itself reveals extraordinary detail. Temperature variations across the sky show tiny fluctuations in density, the seeds of all future cosmic structure. These variations measure about 1 part in 100,000. Regions slightly denser than average would eventually collapse under gravity to form galaxies. Regions slightly less dense would become the voids between galaxy clusters. The entire large-scale structure of today's universe traces back to these microscopic fluctuations visible in the ancient light. Looking at the cosmic microwave background means looking at the oldest possible image of the universe. It represents baby pictures of the cosmos, taken when everything was simpler, smoother, more uniform. Since that moment, gravity has amplified the small variations into the magnificent complexity visible today. But that ancient light also reveals something else. The universe at that early time was already enormous, already expanding, already following the rules that govern it today. The cosmic microwave background confirms the universe had no center even then, yet scientists hope to see farther back using other signals. Gravitational waves and neutrinos can pass through the plasma that trapped light. These particles could carry information from even earlier moments, potentially from the first second after the universe began. Future detectors might pierce the plasma curtain using these alternative messengers. But for now, the cosmic microwave background marks the limit of what you can see. It defines the practical edge of your observable universe. The sky glows with invisible fire. Point any radio telescope at empty space, away from planets, stars, or galaxies, and you detect radiation. Not random noise, but a precise signal with exact properties. This radiation arrives from every direction simultaneously, forming a spherical shell around Earth. It represents the oldest light in the universe, stretched by expansion into microwave wavelengths. Cosmologists call it the cosmic microwave background, and it marks the edge of observational reality. This radiation began its journey 13.8 billion years ago. Well, almost 13.8 billion. The universe was 380,000 years old when this light was released, making the radiation 13.79962 billion years old. That tiny difference matters because it reveals something crucial. The universe had already expanded significantly before light could travel freely. The cosmic microwave background comes from a shell of space that was much closer to Earth when the light was emitted. Current distance to that shell measures about 46 billion light-years. But when the radiation left, the entire observable universe was just 42 million light-years across. Expansion has stretched everything by a factor of roughly 1,100 since then. The light itself has stretched by the same amount. Photons that left as visible or ultraviolet light now arrive as microwaves, with wavelengths about 1 millimeter long. This stretching reveals the expansion history of the universe. Temperature tells the same story. When the cosmic microwave background was released, the universe blazed at about 5,400 degrees, hot enough to glow orange-red. Today, that radiation measures just 2.7 degrees above absolute zero, colder than the vacuum of space. The cooling tracks expansion precisely. As space grows, radiation within it loses energy. The wavelengths stretch, and the temperature drops in perfect proportion to the expansion. But temperature varies slightly across the sky. One direction might be 2.726 degrees, while another measures 2.724 degrees. These tiny variations, measured in millionths of a degree, reveal the structure of the early universe. Hotter spots represent regions slightly denser than average. Cooler spots show regions slightly less dense. Gravity has been amplifying these variations for 13.8 billion years, transforming them into the galaxies and cosmic voids we see today. The cosmic microwave background also reveals the geometry of space itself. Hot and cold spots appear at specific angular sizes across the sky, measuring about 1 degree across. This size depends on the curvature of space. If the universe curved like a sphere, the spots would appear larger. If it curved like a saddle, they would appear smaller. Observations show the spots match predictions for flat space almost perfectly. The universe appears to have exactly zero curvature, within measurement error of 0.4%. This flatness reveals something extraordinary about cosmic density. For space to be flat, the universe must contain a precise amount of matter and energy. Too much and space curves inward like a sphere. Too little and it curves outward like a saddle. The measured density sits right at the critical value, balanced on a knife edge. This suggests either remarkable cosmic coincidence or some underlying principle that forced the universe to flatness. The cosmic microwave background contains more information than astronomers have fully extracted. Future measurements will reveal smaller temperature variations, more detailed patterns, hidden signals buried in the ancient light. Each new detail refines our understanding of cosmic history. But the fundamental limit remains fixed. You cannot see past this wall of light. The cosmic microwave background defines the edge of electromagnetic observation. Behind it lies the plasma era, forever hidden from direct view. Your universe has two edges, and they tell different stories about time. The first edge, the particle horizon, defines how far light could have traveled since the universe began. It represents the past, marking the boundary of everything whose light has had time to reach you. Currently sitting about 46 billion light-years away, this horizon expands constantly as the universe ages. Every second that passes, light from more distant regions completes its journey and enters your observable sphere. The particle horizon grows, revealing new cosmic territory. The second edge, the event horizon, defines something stranger. This boundary marks the farthest distance from which light emitted right now could ever reach you in the future. It represents a division between galaxies you can still contact and galaxies forever beyond reach. Currently sitting about 16 billion light-years away, this horizon is much closer than the particle horizon. But here comes the disturbing part. The event horizon is not expanding. In a universe dominated by dark energy, it actually shrinks. These two horizons move in opposite directions. As time passes, the particle horizon expands outward. You see light from more distant regions that released it long ago. Meanwhile, the event horizon contracts inward. Fewer galaxies remain contactable with each passing moment. Eventually, billions of years from now, the two horizons will converge. The particle horizon will reach its maximum size, while the event horizon shrinks to a minimum. After that point, your observable universe stops growing. Picture what this means for cosmic observation. Right now, you can see galaxies whose light has been traveling for over 13 billion years. These galaxies sit more than 30 billion light-years away due to expansion. Their ancient light shows them as they were in the early universe, young and actively forming stars. But these same galaxies crossed the event horizon long ago. Light they emit today will never reach Earth. You are watching a delayed broadcast of their past, but their present remains forever unknowable. Thousands of galaxies cross the event horizon every single day. They slip beyond the boundary, where communication becomes impossible. You can still see their old light for billions of years to come, but new light from them will never arrive. As their final ancient photons reach Earth and no replacements follow, these galaxies will gradually fade from view. Their images will redshift into invisibility, stretched by expansion until detecting them requires impossible sensitivity. This creates a bizarre form of cosmic blindness. Imagine watching a distant spaceship through a telescope. The ship crosses a threshold where signals can no longer escape. You continue seeing it because old light keeps arriving, but that light shows increasingly outdated information. You watch the ship as it was 1 minute ago, then 5 minutes ago, then an hour ago. The image redshifts, dims, and freezes at the moment of crossing. You never see what happens after. The ship appears locked at the boundary forever, fading into darkness. Galaxies beyond the event horizon behave exactly this way. You see them as they were when light escaped their local region, before space expansion trapped subsequent photons. Their images freeze, redshift, and vanish. The observable universe loses galaxies permanently, even while remaining infinite in extent. Your visible cosmos shrinks, even as total cosmic space continues growing. You become increasingly isolated in an expanding yet emptying observable sphere. This represents the far future of observation. Billions of years ahead, astronomers will detect fewer galaxies than you can see today. Their observable universe will contain less variety, fewer examples of cosmic structure, reduced astronomical diversity. Some types of galaxies visible now will have faded completely. Future civilizations might develop cosmology with incomplete data, missing crucial examples of cosmic evolution that crossed the event horizon before their species emerged. The two horizons define your window into infinity. One expands, revealing the past. The other contracts, sealing off the future. Every minute, light from about 20 million galaxies crosses an invisible threshold and begins losing its battle against space. These photons will never reach Earth. They launch toward us at maximum cosmic speed, racing across expanding space, only to drift farther away with every second that passes. The expansion of the universe overwhelms their forward progress. They fight against a current stronger than their speed, making negative progress despite traveling as fast as physics allows. This defines your future horizon, the boundary beyond which the cosmos becomes unreachable. The event horizon currently measures about 16 billion light-years away, but this distance will change. In a universe filled only with matter, the event horizon would sit infinitely far away. Every galaxy, no matter how distant, would eventually become observable if you waited long enough. Light from anywhere could reach you, given sufficient time. But our universe does not contain only matter. Dark energy dominates the cosmic inventory, making up roughly 68% of all energy density. Dark energy has a strange property. Unlike matter or radiation, which dilute as space expands, dark energy maintains constant density. Create new space, and you create new dark energy to fill it. This violates intuition. Normal stuff spreads thinner as volume increases. Dark energy does not. The total amount of dark energy in the universe increases as expansion creates more volume. This accelerates the expansion itself. More space means more dark energy, means faster expansion, means even more space in a runaway feedback loop. This acceleration changes cosmic horizons dramatically. In an accelerating universe, the event horizon converges to a fixed distance. Currently at about 16 billion light-years, it will asymptotically approach 17.6 billion light-years over cosmic time. This represents the maximum distance from which light emitted at any future moment can reach us. Galaxies beyond this ultimate horizon are forever beyond contact, no matter how long you wait or what signals you send. Picture the implications stretching across deep time. Right now, you can see about 2 trillion galaxies. That number will decline. Over the next 100 billion years, galaxies will cross the event horizon and fade from view as their final photons arrive. The observable universe will empty out. Eventually, only galaxies bound to our local gravitational group will remain visible. Everything else will have redshifted into invisibility, their light stretched into undetectable wavelengths by relentless expansion. Future civilizations will inhabit a lonelier cosmos. Imagine astronomers 100 billion years from now, evolving on a planet, orbiting a star in our galaxy or nearby. They look at the night sky and see almost nothing beyond their local cluster. The cosmic microwave background will have redshifted into radio waves, then into wavelengths too long to detect. Evidence for the Big Bang will have vanished. These future scientists might conclude they live in a static, eternal universe containing only their local galaxies surrounded by infinite darkness. They would be completely wrong. The universe beyond their horizon continues expanding, filled with countless galaxies they cannot see. But they would have no way to discover this truth. All evidence exists beyond their observational reach. They could develop sophisticated theories, build powerful instruments, conduct careful observations, and still miss the larger cosmic reality. Their observable universe tells an incomplete story. This raises an unsettling question about our own era. What if we are already in such a position? What if crucial evidence about cosmic structure exists beyond our current horizon, forever hidden? The universe we observe might be unrepresentative of the full cosmos. Patterns visible to us might be local accidents, not universal features. We assume our observable region shows typical cosmic properties, but we cannot verify this assumption. Infinity beyond our horizon remains unknowable. The shrinking event horizon guarantees increasing isolation. Dark energy seals off more of the universe with each passing moment. But even within our observable sphere, something else defines the cosmic boundary. Space can curve in 3 possible ways, and only one allows infinity. Imagine walking forward on a perfectly flat surface forever. You never return to your starting point. You never encounter an edge. The surface extends infinitely in all directions. This represents flat geometry, where parallel lines stay parallel and triangles always have angles summing to 180 degrees. Flat space follows the rules you learned in school, the geometry of Euclid that describes everyday experience. Now picture walking on the surface of a sphere. Travel in any direction, and you eventually return to where you started. The surface has no edge, no boundary, yet it contains finite area. Parallel lines drawn on a sphere eventually meet. Triangles have angles summing to more than 180 degrees. This represents positive curvature, where space curves back on itself like the surface of a ball. A universe with positive curvature would be finite in volume, containing only a limited amount of space. Finally, imagine walking on a saddle-shaped surface. This represents negative curvature, where parallel lines diverge, and triangles have angles summing to less than 180 degrees. Space curves outward rather than inward. This geometry also allows infinite extent. You could travel forever without encountering boundaries or returning to your origin. Negative curvature creates infinite space. Just like flat geometry, but with different rules governing shapes and angles. Which geometry describes our universe? Measurements point overwhelmingly toward flatness. Observations of the cosmic microwave background, studies of galaxy clustering, measurements of distant supernovae, all converge on the same answer. The universe appears to be flat within 0.4% measurement accuracy. Space neither curves inward like a sphere nor outward like a saddle. It follows Euclidean rules across cosmic scales. But flatness creates a puzzle. For space to be flat, the universe must contain exactly the right amount of matter and energy. This critical density equals about 6 hydrogen atoms per cubic meter on average. Measure more density and space curves inward, creating positive curvature. Measure less and space curves outward, creating negative curvature. The actual density sits right at this critical value, balanced impossibly precisely. This balance seems too perfect to be coincidental. Early in cosmic history, even tiny deviations from flatness would have grown rapidly. If the universe started slightly curved, expansion would have amplified that curvature. By now, space should show obvious curvature, either closing back on itself or opening dramatically. Yet observations show near-perfect flatness. Something must have driven the universe toward this special geometry. Cosmic inflation provides the most popular explanation. This theory proposes that the universe underwent a brief period of exponential expansion during its first fraction of a second. Space grew by at least a factor of 10 to the power of 26, smoothing out any initial curvature. Picture inflating a balloon to enormous size. The surface appears increasingly flat to an observer sitting on it. Inflate the universe sufficiently, and any curvature becomes undetectable. The observable universe represents a tiny patch of a much larger cosmos, appearing flat for the same reason Earth's surface appears flat from ground level. Flatness strongly suggests infinite extent. If space has zero curvature and extends forever in all directions, the universe contains infinite volume. Infinite space means infinite matter, infinite galaxies, infinite stars. Everything that can happen does happen somewhere. Every possible arrangement of matter exists. Every variation on physical law allowed by quantum mechanics manifests in some region. Infinity contains everything, but flatness alone does not guarantee infinite extent. Space could be flat yet finite if it has unusual topology, if it connects back on itself in strange ways. Picture a sheet of flat paper. Now connect opposite edges. You create a cylinder, a shape with flat geometry but finite area. Connect the remaining edges and you create a torus, shaped like a donut surface. The torus has flat geometry everywhere, yet it contains only finite area. You can travel around it and return to your starting point, despite walking on a flat surface. Three-dimensional space could have similar topology. The universe might be a three-dimensional torus, flat everywhere, but finite in volume. Travel far enough in any direction, and you would return to your starting location. Light could orbit the cosmos, creating multiple images of the same galaxy at different distances. Astronomers have searched for such patterns without success. Current observations rule out small toroidal universes, but cannot eliminate this possibility if the topology operates on scales larger than the observable universe. Geometry alone cannot tell you whether infinity exists beyond your horizon. Try to measure the distance to a galaxy, and the ruler changes while you are measuring. Imagine holding a tape measure between Earth and a distant galaxy. By the time you read the measurement, the galaxy has moved. Not because it traveled through space, but because space itself grew. The centimeters marked on your tape stretched. The ruler expanded along with the universe. Every unit of distance increased proportionally. This makes cosmic distance fundamentally ambiguous. Astronomers use multiple distance definitions to handle this problem. Co-moving distance measures how far apart objects would be if expansion stopped right now. This distance follows the expansion of space, growing as the universe expands. Proper distance measures the actual separation at a specific moment in time, the length you would measure with a ruler instantaneously placed between 2 points. These two distances differ because expansion is ongoing. Proper distance changes continuously, while co-moving distance accounts for expansion automatically. Light travel distance measures something different again. This represents how far light traveled through space to reach you, not how far the source currently sits. A galaxy whose light took 10 billion years to arrive does not sit 10 billion light years away now. It sits much farther because space expanded during the light's journey. The light travel distance tells you about the age of the light, not the current location of its source. Then there is redshift distance. As light travels through expanding space, its wavelength stretches proportionally to the expansion. Measure how much the wavelength increased, and you can calculate how much the universe expanded during the light's journey. This gives you a dimensionless number called redshift. A galaxy with redshift of 1 emitted light when the universe was half its current size. A galaxy with redshift of 10 emitted light when the universe was 1/11th its current size. Redshift connects directly to expansion history. But converting redshift into distance requires knowing how fast the universe expanded at each moment in the past. This depends on the density of matter, dark energy, and radiation at each epoch. Change the assumed density, and you change the calculated distance. Redshift alone does not tell you how far away something sits. You need additional information about cosmic expansion to convert redshift into distance. All these distance measures complicate cosmic mapping. When astronomers report distances to galaxies, they must specify which definition they are using. A galaxy 13 billion light-years away in light travel distance might sit 30 billion light-years away in proper distance. Same galaxy, same observation, different distances depending on how you define the measurement. The expanding ruler makes cosmic cartography inherently ambiguous. But the worst complication comes from trying to define velocity. How fast is a distant galaxy moving? The answer depends entirely on reference frame. Relative to the space around it, the galaxy might be nearly stationary. Relative to Earth, taking expansion into account, the galaxy recedes at thousands of miles per second. Which velocity is correct? Both are valid in their own framework. Neither is fundamentally more real than the other. This creates the infamous question about faster-than-light expansion. Distant galaxies recede faster than light. Does this violate relativity? No, because special relativity restricts motion through space, not expansion of space itself. The galaxy does not move faster than light through its local space. Space carries it faster than light relative to Earth. Both statements are true simultaneously. The distinction matters only when you specify reference frame clearly. Measuring the universe requires carefully defining what you mean by distance, velocity, and separation. The expanding ruler ensures that simple concepts become complex when applied across cosmic scales. Space itself changes the rules of measurement, transforming geometry from a fixed stage into a dynamic participant in cosmic evolution. Every observation requires accounting for expansion. Every distance measurement depends on cosmic history. Every ruler bends with the fabric of spacetime. Yet despite these complications, astronomers have achieved extraordinary precision. They know the expansion rate to within 1%. They know the distance to the cosmic horizon to within a few percent. They know the age of the universe to within millions of years. The bending ruler did not prevent measurement. It merely required more sophisticated tools. And those tools revealed the universe balances on a knife edge. 6 hydrogen atoms per cubic meter. That represents the critical density, the precise amount of matter and energy required to make space flat. More than 6 atoms and space curves inward, creating positive curvature. Less than 6 atoms and space curves outward, creating negative curvature. This number determines cosmic geometry, cosmic fate, and whether the universe extends infinitely or closes back on itself. The actual density of the universe matches this critical value almost exactly. Measurements show space is flat to within measurement error. This means the average density across the cosmos equals the critical density within a fraction of a percent. Count all the matter, all the dark matter, all the dark energy, divide by volume, and you get 6 hydrogen atoms per cubic meter. This perfect balance seems suspicious. Why would the universe sit precisely at this special value? Early deviations would have grown catastrophically. If the universe started even slightly curved, expansion would amplify that curvature rapidly. Imagine density 1% higher than critical in the first second after the Big Bang. By now, the universe would have collapsed back on itself billions of years ago. Imagine density 1% lower. By now, space would curve so dramatically that galaxies could never have formed. Matter would have spread too thin, gravity too weak, structure too diffuse. Yet the universe sits right at critical density. This fine-tuning problem plagued cosmologists for decades. The balance seemed too perfect, too precise, too unlikely to be coincidental. Either some mechanism forced the universe toward flatness, or we lived in an extraordinarily special cosmos. The first option requires new physics. The second requires accepting cosmic coincidence. Cosmic inflation solved this mystery elegantly. If the universe underwent exponential expansion during its first fraction of a second, any initial curvature would have been stretched to undetectable levels. Picture a balloon with wrinkles. Inflate it sufficiently, and the wrinkles smooth out. The surface becomes flat to any observer sitting on it. Inflate the universe by at least a factor of 10 to the 26th, and the same thing happens. Any original curvature gets diluted below detectability. This explains observed flatness naturally. The universe did not need to start at critical density. It could have begun with any density whatsoever. Inflation drove it toward flatness automatically. After inflation ended, the universe continued expanding more slowly, preserving the flatness created earlier. We measure near critical density today because inflation forced space toward zero curvature during cosmic birth. But here comes a darker implication. If inflation drove the universe to flatness, space probably extends infinitely. The observable universe represents a tiny patch of a vastly larger cosmos, inflated to enormous size. Most of that cosmos lies beyond any horizon, forever unobservable. Infinity exists beyond your reach, guaranteed by the same physics that flattened space. Critical density also determines cosmic fate. If density exceeds critical, the universe eventually collapses. Gravity overwhelms expansion, pulling everything back together in a big crunch. If density falls below critical, expansion continues forever, accelerating as matter dilutes. If density equals critical exactly, expansion continues forever, but gradually slows towards zero velocity after infinite time. The universe coasts, neither collapsing nor accelerating indefinitely. Our universe does none of these things. Observations reveal accelerating expansion driven by dark energy. This mysterious component acts like anti-gravity, pushing space apart faster over time. Dark energy dominates the density budget, making up 68% of critical density. Matter and dark matter contribute 32%. Together, they sum to exactly critical density, making space flat while driving accelerated expansion. This creates a new puzzle. Why does dark energy have precisely the density needed to make total density critical? This represents another fine-tuning problem, another cosmic coincidence requiring explanation. The density of dark energy could have been any value. Why does it equal exactly the amount needed to flatten space when combined with matter density? No one knows. The universe balances at critical density for reasons that remain mysterious. Inflation explains why matter density sits near critical. Dark energy explains accelerated expansion. But why these two components sum to exactly critical density remains unexplained. The knife-edge balance suggests some underlying principle, some deeper law that forces this relationship. Until we discover that principle, the coincidence stands as one of cosmology's great mysteries. Yet this balance defines your observable universe completely. Critical density means flat space means possible. Infinity means an infinite cosmos. For one tiny fraction of a second, the universe exploded faster than physics should allow. Between roughly 10 to the minus 35 and 10 to the minus 32 seconds after the Big Bang, space expanded by at least a factor of 10 to the 26th. The entire observable universe grew from smaller than an atom to larger than a grapefruit in less time than a photon takes to cross a proton. This represents exponential expansion, where size doubles repeatedly at fixed intervals. The universe doubled again, at least 90 times in rapid succession. Nothing in normal physics predicts this behavior. The standard Big Bang model describes steady expansion that gradually slows under gravity's pull. Inflation requires something different, a mysterious energy field that dominated early cosmic dynamics. This inflaton field generated enormous repulsive pressure, driving expansion to exponential rates. For a brief moment, this field overwhelmed all other forces, all other energy, all other cosmic components. Inflation solves multiple cosmic puzzles simultaneously. First, it explains flatness. Exponential expansion stretches space like a balloon, smoothing any initial curvature to undetectable levels. Second, it explains uniformity. The cosmic microwave background has the same temperature in all directions to 1 part in 100,000. Without inflation, opposite sides of the sky would have been causally disconnected, never in contact, unable to reach temperature equilibrium. Inflation stretched a tiny region large enough to encompass the entire observable universe, creating uniform conditions everywhere. Third, inflation explains the origin of cosmic structure. Quantum fluctuations in the inflaton field created microscopic density variations. These quantum ripples got stretched to cosmic scales by exponential expansion, frozen into the fabric of space as inflation ended. Gravity amplified these fluctuations over billions of years, transforming them into galaxies, clusters, and cosmic voids. All large-scale structure traces back to quantum fluctuations during inflation, submicroscopic variations magnified to intergalactic proportions. But inflation creates a staggering implication for cosmic size. If the observable universe expanded by a factor of 10 to the 26th, the full universe must be vastly larger. The region we can see represents a tiny patch of a much bigger cosmos. Think of Earth's surface. You can only see to the horizon, a few miles in any direction. But Earth extends far beyond your horizon. Similarly, the observable universe represents a small fraction of total space. Inflation likely created a cosmos many orders of magnitude larger than the observable region. How much larger? Conservative estimates suggest the full universe measures at least 10 to the 23rd times larger than the observable portion. That means, if the observable universe was a single atom, the full cosmos would be many times larger than the observable universe itself. Other estimates push this much higher, suggesting the true universe might be effectively infinite for all practical purposes. Inflation also suggests the universe is truly infinite, not just very large. If space has zero curvature, as observations indicate, and if inflation drove that flatness, then space most likely extends infinitely. The physics of inflation predicts infinite extent as the natural outcome. Finite universe models require special conditions, unusual topology, or fine-tuned parameters. Infinity represents the generic prediction of inflationary cosmology. This raises profound implications. If the universe is infinite, it contains infinitely many galaxies, infinitely many stars, infinitely many planets. Quantum mechanics ensures that only finite variations exist in any finite volume. With infinite volume, every possible variation must occur. Somewhere in the infinite cosmos, there exists a galaxy identical to the Milky Way. Somewhere exists a planet identical to Earth. Somewhere exists a person identical to you, living a life identical to yours. These are not possibilities. These are guarantees of infinite space. In an infinite universe, everything that can happen does happen, repeated infinitely many times across infinite space. Every configuration of matter allowed by physics exists somewhere. Every variation on cosmic history unfolds in some region. Every choice you could have made, every alternate path your life could have taken, actually occurs in some distant location. Infinity contains all possibilities, but here comes the most disturbing part. Most physicists expect inflation is not a one-time event. The inflaton field probably did not turn off everywhere simultaneously. Instead, inflation likely ended in some regions, while continuing in others. Those regions where inflation continues keep expanding exponentially, spawning new regions where inflation ends. This creates eternal inflation, a process that never stops, continually generating new inflating regions. Each region where inflation ends becomes a bubble universe with its own properties. Our observable universe represents one such bubble. Beyond our cosmic horizon, countless other bubbles exist, each with potentially different physics, different constants, different laws. This creates a multiverse, an ensemble of universes vastly larger than any single universe. The multiverse might itself be infinite, containing infinite variations on cosmic laws. Inflation transforms the question from whether one universe is infinite to whether infinitely many universes exist. Space can be flat, yet finite if it wraps around itself in hidden dimensions. Picture a video game character running across the screen. Move off the right edge and you reappear on the left. The screen has finite width, yet the character never encounters a boundary. The surface wraps, connecting opposite edges seamlessly. This creates what mathematicians call a non-trivial topology, where space loops back on itself. The screen remains flat, in the sense that parallel lines stay parallel, but it contains only finite area. Three-dimensional space could behave the same way. Imagine traveling in one direction for billions of light years. Instead of continuing forever, you eventually return to your starting point. Space wraps around itself like a three-dimensional version of the video game screen. The universe would be finite in volume but still have no edge, no boundary, no place where space stops. You could travel forever in any direction, eventually circling back to where you began. This shape is called a three-torus. Two-dimensional version looks like a donut surface. The three-dimensional version has no simple visualization because it requires 4 dimensions to embed properly. But mathematically it is well defined and perfectly consistent with flat geometry. Every point on a torus has 0 curvature. Parallel lines stay parallel locally, yet the space has finite volume and connects back on itself globally. Could the universe be a giant cosmic donut? Observations place limits on this possibility. If space wrapped around on scales smaller than the observable universe, we would see multiple images of the same galaxies at different distances. Light from a single galaxy could reach us from multiple directions, having traveled different paths around the cosmic loop. Astronomers have searched for such patterns without success. Current observations rule out toroidal topology smaller than the observable universe, but they cannot rule out larger topology. If space loops on scales bigger than 92 billion light-years, light has not had time to complete a circuit. We would see no repeating patterns, no multiple images, no direct evidence of wrapping. The topology could exist beyond our horizon, forever undetectable from inside the observable region. The universe could be a giant torus, many times larger than what we can see. This creates an odd situation. Space could be flat, satisfying all observational tests, yet still be finite. The universe would contain only limited volume, limited galaxies, limited matter, but that limit would be so large compared to the observable universe that we could never detect it. For all practical purposes, such a universe would appear infinite, even though technically it is not. Other topologies are possible as well. Space could connect back on itself in more complicated ways, creating shapes mathematicians call multi-handle, tori, or other exotic structures. Each topology produces different patterns of cosmic structure, different statistical properties in galaxy distributions, different signatures in the cosmic microwave background. Cosmologists have searched for these signatures without finding convincing evidence. The simplest explanation remains infinite flat space. Observations show 0 curvature within measurement error. Theory predicts infinite extent for flat, simply connected space. Exotic topologies require special conditions, unusual physics, or fine-tuned parameters. Infinity represents the generic, expected outcome given observed flatness. But topology remains a possibility, a loophole allowing finite space within flat geometry. This matters for the question of cosmic uniqueness. If the universe is infinite, everything possible happens somewhere. If the universe is finite, even very large, only limited possibilities occur. The difference matters for questions about probability, fine-tuning, and cosmic coincidence. An infinite universe makes every rare event common somewhere. A finite universe keeps rare events truly rare. We may never know which case applies. If topology operates on scales larger than the observable universe, it remains forever beyond detection. We could develop arbitrarily sophisticated measurements, build impossibly powerful instruments, wait billions of years for light to travel farther, and still miss large-scale topology. The question might be fundamentally unanswerable from within the cosmos. Yet the question shapes how we think about infinity. Does space extend forever, or does it loop back on itself? Does the universe contain infinite matter or finite matter? Are we one possibility among infinite variations, or one configuration in a large but limited set? The answers depend on whether space wraps in ways we cannot detect. For now, flat geometry suggests infinity but cannot guarantee it. The universe must be one of three fundamental forms, and each determines a different fate for existence. A spherical universe curves inward on itself like the surface of a ball. Travel in any direction and you eventually return to your starting location, having circumnavigated cosmic space. This geometry contains finite volume with no boundary. Space curves back on itself, creating a closed cosmos where parallel lines eventually meet. Triangles drawn across cosmic distances have angles summing to more than 180 degrees. Gravity wins in this scenario. The universe eventually stops expanding, reverses direction, and collapses back into a singularity. A hyperbolic universe curves outward like a saddle shape. Parallel lines diverge as they extend into distance. Triangles have angles summing to less than 180 degrees. Space extends infinitely in all directions, opening wider as you move farther from any point. This represents negative curvature, where expansion overwhelms gravity completely. The universe expands forever, accelerating as matter dilutes. Space grows colder, darker, emptier across eternal time. Infinite volume guarantees infinite extent. A flat universe sits precisely between these extremes. Space has zero curvature. Parallel lines stay parallel forever. Triangles have angles summing to exactly 180 degrees. The geometry follows Euclidean rules across cosmic scales. This represents the knife-edge case where gravity and expansion balance perfectly. The universe expands forever, but at a gradually slowing rate. In the limit of infinite time, expansion velocity approaches but never reaches zero. Flat space typically implies infinite extent, though exotic topologies can create finite flat universes. Which shape describes our cosmos? Multiple independent observations converge on the same answer. The cosmic microwave background reveals temperature fluctuations with specific angular sizes. These sizes depend directly on spatial curvature. Measure hot and cold spots at 1 degree across, and space is flat. Larger spots indicate positive curvature, smaller spots indicate negative curvature. Observations show spots measuring almost exactly 1 degree, consistent with flat geometry. Galaxy surveys confirm this conclusion from different evidence. The large-scale distribution of galaxies creates patterns sensitive to curvature. Statistical analysis of galaxy clustering matches predictions for flat space within narrow error margins. Distant supernova observations provide yet another independent check. The brightness of exploding stars at various distances depends on cosmic geometry. These measurements also point toward flatness. All evidence indicates zero curvature within 0.4%. The universe appears to be flat to extraordinary precision. This flatness strongly suggests infinite extent, though it cannot prove infinity conclusively. Space could wrap around itself on scales larger than the observable universe, creating finite volume within flat geometry. But the simplest interpretation remains infinite flat space, extending forever. Positive and negative curvature are essentially ruled out. If space had positive curvature sufficient to close the universe, we would detect it easily. The observable universe would represent a significant fraction of total space. The cosmic microwave background would show clear signatures of closure. None appear. Similarly, strong negative curvature would create detectable patterns in cosmic structure. Observations show no such patterns. Space sits remarkably close to perfect flatness. This flatness creates the cosmic coincidence problem. Why does the universe have exactly the density needed to make space flat? Why not slightly more, creating positive curvature? Why not slightly less, creating negative curvature? The balance seems too precise to be accidental. Either some mechanism forces the universe toward flatness, or we live in an extraordinarily special cosmos. Inflation provides the most convincing mechanism, driving space towards zero curvature during exponential expansion. But inflation also predicts something more unsettling. If inflation drove the universe to flatness by stretching it enormously, the total cosmos must be vastly larger than the observable portion. The region we can see represents a tiny patch of a much bigger universe. And that bigger universe is most likely infinite, extending forever beyond any horizon. The three possible shapes narrow to one, and that one shape points toward infinity. The geometry of everything determines whether existence is finite or endless. Geometry tells you how space curves, but topology tells you how space connects. You can know that space is flat, that curvature equals zero everywhere, and still not know whether the universe is finite or infinite. Geometry measures local properties, how shapes behave in small regions. Topology measures global properties, how space connects to itself across cosmic distances. Two universes can have identical geometry, but completely different topology, like a flat sheet of paper versus a flat torus. This separation between geometry and topology creates a loophole. All observations confirm flat geometry. The cosmic microwave background, galaxy clustering, supernova distances, every measurement points towards zero curvature. Scientists know the universe is flat within measurement error, but this does not prove infinite extent. Space could be flat everywhere, yet still loop back on itself, creating finite volume without any curvature. The observable universe alone cannot distinguish these possibilities. Consider how light travels through different topologies. In simply connected infinite space, light from any source travels in straight lines forever, never returning to its origin. In a toroidal universe, light can orbit the cosmos, potentially creating multiple images of the same object. Photons from a single galaxy might reach Earth from several directions, having taken different paths around cosmic loops. Astronomers would see copies of galaxies at various distances, like reflections in a hall of mirrors. Searches for these patterns have found nothing. Scientists have looked for matching circles in the cosmic microwave background, signatures that would reveal space wrapping back on itself. They have searched for duplicate galaxy patterns, identical arrangements appearing in different directions. They have analyzed statistical properties of cosmic structure for hints of non-trivial topology. No convincing evidence has emerged. The universe appears simply connected, not wrapped or looped. But absence of evidence is not evidence of absence when topology operates beyond the horizon. If space loops on scales larger than 92 billion light-years, light has not completed a circuit. We would see no repeating patterns because photons have not yet traveled far enough to return from the opposite side. The topology could exist beyond detection range, forever hidden by the finite age of the universe. We might live in a finite cosmos and never know it. This matters for fundamental questions about existence. In an infinite universe, every possible configuration of matter occurs somewhere. Quantum mechanics limits the number of distinct arrangements in any finite volume. With infinite volume, repetition becomes inevitable. An infinite cosmos contains infinite copies of you, living infinite variations of your life. In a finite universe, even very large, uniqueness remains possible. You might be the only version of yourself that exists. Topology also affects cosmic evolution in subtle ways. A toroidal universe has finite volume, but no center and no edge. Gravity acts globally, influenced by matter distribution everywhere. This creates correlations in cosmic structure across scales comparable to the topology. A simply connected infinite universe has no such global effects. Local physics determines local structure without distant influence. These differences might appear in subtle patterns, but only if we could observe scales comparable to the topology. Current observations place lower limits on possible topology size. If the universe loops back on itself, the loops must be larger than the observable region. Otherwise, we would detect repeating patterns. The cosmos must be at least 92 billion light-years in circumference for each topological direction. This makes it larger than everything we can see, even if ultimately finite. For practical purposes, such a universe would appear infinite from our limited perspective. Mathematics allows many exotic topologies. Space could wrap in complicated ways, creating multi-handled structures or twisted orientations. Each topology produces different global properties while maintaining local flatness. Most of these possibilities seem physically unmotivated, requiring special conditions during cosmic formation. The simplest topology remains simply connected infinite space, but simplicity alone does not guarantee truth. We may never escape the topology trap. If space connects to itself beyond our horizon, we cannot detect it from within the observable universe. We could wait billions of years, build instruments of arbitrary precision, analyze every photon ever received, and still miss large-scale topology. The question might be fundamentally undecidable, forever beyond empirical resolution. Yet the answer determines whether the universe is finite or infinite. Light from galaxies beyond your cosmic horizon will never reach you, but those galaxies exist right now. 46 billion light-years away, in every direction, lies a boundary. On this side, regions whose light has completed its journey to Earth. On that side, regions whose light remains in transit, racing toward us but not yet arrived. And beyond that, regions so distant that light emitted now cannot overcome cosmic expansion. These regions exist. They contain galaxies, stars, planets, potentially life. But they remain forever separated from our observable universe. What fills this unreachable space? Standard cosmology assumes it looks much like our observable region. The same physical laws apply. The same types of galaxies form. The same large-scale structure emerges. Cosmic uniformity suggests that space beyond our horizon resembles space within it. Take a random sample from the observable universe and you probably see typical cosmic properties. Assume the unobservable region has similar characteristics and you make a reasonable extrapolation. But this assumption cannot be verified. Every measurement comes from within the observable sphere. Every observation samples the same cosmic neighborhood. We assume this neighborhood represents the whole, but we cannot check. The universe beyond our horizon might differ dramatically from what we see. Different structure, different galaxy types, different matter distribution. Our observable patch might be atypical, a cosmic fluke surrounded by vastly different conditions. Some models predict real variation beyond the horizon. Eternal inflation suggests our observable universe represents one bubble in a vastly larger multiverse. Different bubbles undergo inflation for different durations, creating regions with different properties. Physical constants might vary. Particle physics might differ. The strength of gravity, the mass of electrons, the speed of light, all could take different values in distant regions. Our observable universe shows one set of cosmic parameters, but infinity beyond the horizon might sample the full range. This creates observer selection effects. We necessarily live in a region where conditions allow observers to exist. Stars must form to create heavy elements. Planets must be stable enough for life. Physical constants must permit chemistry. These requirements filter the regions where observers can emerge. We see cosmic properties compatible with our existence, but this tells us nothing about typical properties across the full universe. Most space might be uninhabitable, with observers concentrated in rare pockets. The cosmological principle assumes uniformity across all scales. This principle states that the universe looks roughly the same from any location, that no position is special or privileged. Our observable region represents a fair sample of the whole. Conditions here match conditions everywhere. This assumption underlies most cosmological models, providing the foundation for predictions and calculations. But it remains an assumption, impossible to verify beyond our horizon. Alternatively, the universe might be fundamentally inhomogeneous at large scales. Perhaps space contains vast regions with different properties, domains larger than our observable sphere. We see only one domain, one particular sample, one local patch. Beyond our horizon, conditions might differ dramatically. This does not violate any known physics. Nothing prevents cosmic inhomogeneity at superhorizon scales. We simply assume uniformity because it seems simpler. Some observations hint at unexpected structure. Large-scale flows of galaxies suggest matter distribution, extending beyond the observable universe. The cosmic microwave background shows subtle asymmetries, cold spots, and hot spots that might indicate external influence. These anomalies remain marginal, possibly statistical flukes, but they raise the possibility that our horizon does not encompass everything relevant to local cosmic structure. Beyond the observable universe lies the unobservable universe. This region exists with certainty. Space extends past our horizon. Galaxies populate that space. Structure continues into the invisible distance. But we cannot measure it, cannot observe it, cannot interact with it. The unobservable universe might be vastly larger than the observable portion. If inflation stretched space enormously, the full cosmos could be many orders of magnitude bigger than what we can see. And if the universe is infinite, the unobservable portion is infinitely larger than the observable part. What exists beyond the wall shapes the ultimate nature of reality. If the universe extends forever, you exist in countless locations right now. This is not speculation or metaphor. This is mathematical certainty following directly from infinite space combined with quantum mechanics. Quantum theory limits the number of possible configurations in any finite volume. Particles can only arrange themselves in finite ways within a region of space. With infinite volume, configurations must repeat. Somewhere in the infinite cosmos, an identical copy of you sits reading these exact words. The calculation is straightforward and deeply unsettling. Take a volume of space, 100 billion light-years across. This volume contains roughly 10 to the power of 118 particles. Quantum mechanics allows these particles to arrange in about 10 to the power of 10 to the power of 118 different configurations. This number is enormous, but finite. Now consider infinite space containing infinite such volumes. With finite configurations and infinite space, repetition becomes inevitable. The nearest identical copy of you sits about 10 to the power of 10 to the power of 29 meters away. This distance is incomprehensibly large, so vast that standard notation fails. But in an infinite universe, such distances exist. Travel that far and you encounter an exact duplicate of Earth, containing an exact duplicate of you, living an identical life, having identical thoughts. This person is not similar to you. This person is identical, atom for atom, quantum state for quantum state. Farther away, variations appear. A version of you who chose a different career, a version who moved to a different city, a version who made different decisions at crucial moments. An infinite universe contains all possible variations of your life, every path not taken, every alternate choice. These are not parallel universes in the quantum mechanics sense. These are different locations in the same infinite space, separated by unimaginable distances. The implications extend beyond individuals. Somewhere exists an identical copy of Earth, complete with identical history, identical civilizations, identical art and music and literature. Somewhere exists a planet almost like Earth, but with minor differences, where the Roman Empire never fell or where dinosaurs still roam. Somewhere exists every possible variation of Earth allowed by physics and chemistry. Infinite space guarantees infinite planets exploring infinite possibilities. This transforms questions about probability and coincidence. Is the exact arrangement of our solar system unlikely? In a finite universe, perhaps. In an infinite universe, every configuration occurs infinite times. The most improbable arrangement becomes common somewhere. Nothing is truly rare because infinity makes every possibility abundant. Fine-tuning arguments lose force when infinite space guarantees all configurations. But wait, it gets stranger. The copies extend to entire cosmic regions. Somewhere in infinity exists a region 100 billion light-years across, identical to our observable universe in every detail. Every galaxy occupies the same position. Every star follows the same evolution. Every planet forms with identical properties. This region is not similar to ours. It is identical, a perfect copy of everything you can ever observe. How far away does this identical, observable universe sit? The calculation yields a number with more zeros than atoms in your body. The distance is so vast that describing it requires scientific notation stacked multiple layers deep. Yet, in infinite space, this distance exists. Given infinite volume and finite configurations, perfect copies are mathematically guaranteed. Philosophers debate whether these copies count as separate individuals. If two regions of space are identical, do they represent one thing existing in multiple locations or multiple distinct things? Does the version of you 10 to the power of 10 to the power of 29 meters away have the same consciousness, the same identity, the same selfhood, or does spatial separation create genuine multiplicity? These questions have no obvious answers. Physics offers no mechanism for distinguishing identical copies. If two regions have exactly the same quantum state, they are physically indistinguishable. No measurement, no observation, no experiment can tell them apart. They represent perfect replicas, yet they occupy different spatial positions, separated by unimaginable distance. The identical copies exist as separate regions of the same infinite cosmos. Some find this idea comforting. In an infinite universe, you are never truly alone. Countless versions of you exist scattered across infinity, some living identical lives, some living variations. Your existence is not unique or special, but it is inevitable and repeated endlessly. Others find this terrifying. Your choices lack ultimate significance when infinite copies make different choices. Your life becomes one instance among infinite instances. Either way, infinity changes the meaning of existence itself. In finite space, you might be unique. In infinite space, you are common. Watch a galaxy cross the event horizon, and you see it freeze at the boundary forever. The galaxy recedes from Earth at ever-increasing speeds as space expands. At first, light from the galaxy easily overcomes this expansion, arriving regularly with new information about stellar evolution and cosmic chemistry. But as the galaxy moves farther, expansion accelerates. The space between you and that galaxy grows faster each year. Eventually, the recession velocity exceeds light speed. The galaxy crosses the event horizon. What happens to light emitted at that moment? The photons travel toward Earth at maximum cosmic speed, but space carries them backward faster than they advance forward. They make negative progress, drifting farther from Earth with each passing second despite racing toward us. These photons will never arrive. The galaxy has crossed into unreachable territory. Light it emits now remains trapped beyond the horizon, unable to overcome expansion, but you continue seeing the galaxy for billions of years afterward. Light emitted before the crossing still approaches Earth. Photons that left the galaxy when recession velocities were lower can complete their journey. They arrive carrying increasingly outdated information. You see the galaxy as it was 1 million years before crossing, then 10 million years before, then 100 million years before. The stream of arriving photons shows progressively older images. This creates a bizarre temporal effect. The galaxy appears to slow down as it approaches the horizon. Its evolution freezes. Stars stop forming. Supernovae that should occur never appear. The galaxy's image locks at the moment of crossing, showing eternal snapshots of its state at the event horizon. You never see what happens after. The present and future of that galaxy remain permanently hidden. Meanwhile, the light itself changes dramatically. Expansion stretches photon wavelengths as they travel through growing space. Light that left the galaxy as ultraviolet arrives as infrared. Light that left as visible red arrives as microwave. The longer the photons spend in transit, the more they redshift. Images of the galaxy gradually shift through the spectrum, becoming redder, dimmer, longer in wavelength. Eventually, the light becomes undetectable. Wavelengths stretch beyond what any conceivable instrument can measure. The galaxy fades from view, not because it stops emitting, but because its light redshifts into invisibility. The final photons arrive so stretched, so dim, so depleted of energy that detecting them becomes impossible. For all practical purposes, the galaxy disappears from the observable universe. Yet the galaxy itself continues existing beyond your horizon. Stars form and explode. Gas clouds collapse and scatter. Planets orbit in systems you will never see. The galaxy undergoes normal cosmic evolution, following the same physics as galaxies within your reach. Nothing special happens at the event horizon from the galaxy's perspective. Local physics continues unchanged. Only the connection to distant observers breaks. Now, consider this from the galaxy's viewpoint. Observers in that galaxy see Earth recede past their event horizon simultaneously. They watch our galaxy freeze at their boundary, images locked at the moment of crossing. They see our light redshift into invisibility. To them, Earth has left their observable universe, just as they have left ours. Both perspectives are equally valid. Event horizons are observer-dependent boundaries, not objective features of space. This creates a strange symmetry. We lose access to distant galaxies. They lose access to us. The separation is mutual, the isolation symmetric. Neither location is special. The event horizon simply marks where expansion overwhelms light speed for any pair of observers. As the universe ages, more galaxy pairs become mutually unreachable. The cosmic neighborhood shrinks for everyone. Billions of years in the future, the observable universe will contain far fewer galaxies. Everything beyond our local gravitational group will have faded from view. Future astronomers will detect only nearby galaxies, bound together by gravity too strong for expansion to overcome. They might conclude the universe consists of their local cluster surrounded by infinite empty space. They would be wrong, but all contrary evidence would lie beyond their horizon. Information loss accelerates as the event horizon contracts. Dark energy drives expansion faster over time. This brings the event horizon closer, shrinking the sphere of reachable space. More galaxies cross the boundary each moment. The cosmic neighborhood empties at an increasing rate. Eventually, only gravitationally bound structures remain visible. Everything else vanishes beyond the contracting horizon. You are watching the universe disappear in real time, galaxy by galaxy. The frozen images at the horizon mark the last glimpses of cosmic regions you can never visit. Every photon that crosses space loses energy to expansion. As space stretches, light stretches with it. Wavelengths increase proportionally to the growth of the universe. A photon emitted as blue light might arrive as red. A photon emitted as red might arrive as infrared. A photon emitted as infrared might arrive as microwave. The transformation continues relentlessly as long as light travels through expanding space. This process is called cosmological redshift, and it determines what you can observe. Redshift measures how much the universe expanded during a photon's journey. Scientists express redshift as a number indicating wavelength change. Redshift 0 means no change. Redshift 1 means wavelength doubled. Redshift 2 means wavelength tripled. The highest redshift galaxies observed sit around redshift 13. meaning the universe expanded 14-fold since their light was emitted. These galaxies appear as they were just a few 100 million years after the Big Bang. But redshift does more than change color. Energy decreases as wavelength increases. A photon with double the wavelength has half the energy. A photon with triple the wavelength has 1/3 the energy. As galaxies recede and their light redshifts, each arriving photon carries less energy than when it was emitted. The light becomes dimmer not only because of increasing distance, but also because individual photons weaken. Now combine redshift with time dilation. Events in distant galaxies appear to run slower from our perspective. A supernova explosion that takes 3 weeks locally appears to last 6 weeks at redshift 1, 9 weeks at redshift 2. The expansion of space dilates time for distant objects, making their evolution appear to proceed in slow motion. This further reduces the rate at which photons arrive. Not only does each photon carry less energy, but fewer photons arrive per second. The combined effect is devastating for observation. A galaxy at high redshift appears dramatically fainter than an identical galaxy nearby. The light loses energy to redshift. Time dilation reduces photon arrival rates. Geometric spreading across increased distance further dilutes the light. All three effects multiply together, making distant galaxies extraordinarily difficult to detect. The most distant galaxies observable today required years of telescope exposure time to capture enough photons for clear images. But there is a limit beyond which detection becomes impossible. As galaxies recede past the event horizon, their light redshifts toward infinity. Wavelengths grow without bound. Energy approaches zero. Photon arrival rates drop toward nothing. Eventually, the combined factors reduce light intensity below any possible detection threshold. The galaxy fades into invisibility not because it stops emitting, but because its light becomes undetectable. This fate awaits every galaxy beyond our local group. Over billions of years, each distant galaxy will cross the event horizon and fade from view. You are already seeing the beginning of this process. The most distant galaxies visible today are barely detectable with the most powerful telescopes. Their light arrives weakened by extreme redshift, diluted by time dilation, spread thin by cosmic expansion. These galaxies hover at the edge of observability. Future telescopes might push detection limits farther, but only marginally. Each increase in sensitivity reveals slightly more distant galaxies at slightly higher redshift. But physical limits prevent infinite progress. Photon energy cannot decrease below the cosmic microwave background temperature. Detection becomes impossible when galaxy light redshifts to wavelengths longer than the background radiation. At that point, galaxies become indistinguishable from the faint glow filling all of space. This represents the ultimate horizon of electromagnetic observation. Even with perfect instruments, infinite sensitivity, and unlimited observation time, you cannot see past where galaxy light redshifts into the microwave background. The universe becomes opaque not because matter blocks the view, but because signal strength drops below the noise floor. Distant galaxies exist, emit light, and undergo normal evolution, but their radiation arrives so weakened that extracting meaningful information becomes physically impossible. The observable universe has a soft edge defined by redshift fade. There is no sharp boundary where galaxies suddenly disappear. Instead, they gradually fade with increasing distance, becoming dimmer, redder, more time-dilated, harder to detect. The farthest observable galaxies represent the limit where light remains barely detectable above background. Beyond that limit, countless galaxies exist but remain invisible, their light stretched into undetectable wavelengths. This creates asymmetry between looking and reaching. The particle horizon defines how far you can see using ancient light emitted long ago. The event horizon defines how far you can reach using signals sent now. The redshift fade defines how clearly you can observe objects at various distances. These three boundaries create nested limits, each constraining different aspects of observation. Together, they define the effective edge of your observable universe. and that edge moves inward as dark energy accelerates expansion. Galaxies you can see today will eventually fade beyond detectability. 100 billion years from now, most galaxies will have vanished from the night sky. Imagine distant future observers, perhaps emerging on planets orbiting stars formed from recycled stellar material long after our time. These observers develop astronomy, build telescopes, study the cosmos. They see a profoundly different universe than we observe today. Their night sky contains only the galaxies of their local group, perhaps 50 galaxies bound together by mutual gravity. Beyond that, darkness, empty space extending infinitely in all directions. These future astronomers would face a cosmological puzzle with no solution. They would measure the motions of galaxies in their local cluster, finding them gravitationally bound. They would see no other galaxies, no evidence of cosmic expansion, no hints of the Big Bang. The cosmic microwave background would have redshifted into undetectable radio wavelengths. All evidence for modern cosmology would have faded beyond their horizon. They might conclude they live in a static, eternal universe containing one small cluster, surrounded by infinite empty space. They would be completely wrong, but unable to discover their error. All contradicting evidence exists beyond their event horizon. Billions of galaxies continue existing, evolving, forming stars. The universe continues expanding, accelerating under dark energy's influence. But none of this remains observable. The accelerated expansion has carried everything beyond detection range. Future observers see only their local cosmic neighborhood, cut off from the larger universe. This illustrates how cosmological evidence is temporary. We live in a special epoch where the universe reveals itself clearly. The cosmic microwave background remains detectable. Distant galaxies lie within observational range. Evidence for expansion, the Big Bang, cosmic evolution, all remain accessible, but this window is closing. As expansion accelerates, evidence fades. Future observers will lack the data needed to reconstruct cosmic history. Some argue we might already be in such a position. What if crucial evidence about the universe existed in the past, but has faded beyond our horizon? Early epochs might have displayed features no longer observable. The first stars, the first galaxies, the detailed structure of cosmic inflation, all might have left signatures that redshifted into undetectability before human observers emerged. We see a universe already partially edited by time and distance. The far future grows progressively lonelier for observers everywhere, not just for our distant descendants, but for every civilization in every galaxy. As the event horizon contracts, each observer loses access to more of the cosmos. Local groups of galaxies remain visible, bound together too tightly for expansion to separate them. But everything beyond slowly fades. The observable universe shrinks for everyone simultaneously. Eventually, only gravitationally bound structures remain visible. Galaxies within the local group will merge over billions of years, eventually forming a single giant elliptical galaxy. Observers in this galaxy will see nothing beyond their merged system. No external galaxies, no cosmic microwave background, no evidence of anything beyond their local structure. They will inhabit an island of matter surrounded by apparent cosmic void. But the void is not empty. Countless galaxies continue existing beyond the horizon. The universe remains full of structure, teeming with stars, possibly alive with civilizations. Nothing changes in the larger cosmos. Only the observational connection breaks. Expansion carries distant regions beyond detection range, creating apparent emptiness where reality remains rich and complex. This raises philosophical questions about the meaning of existence. If something exists but cannot be observed, detected, or interacted with in any way, does it meaningfully exist from your perspective? Future observers cannot confirm that anything lies beyond their local cluster. They might theorize about larger cosmic structure, but they cannot test those theories. The unobservable universe becomes irrelevant to their science. Yet it remains real, filled with galaxies they will never see. Our epoch represents a golden age for cosmology, a brief window where the universe reveals itself. Before us, the cosmos was too young, too hot, too simple to produce observers. After us, the universe will be too old, too expanded, too isolated for observers to see clearly. We exist at the moment when cosmic history remains observable, when evidence for the Big Bang persists, when distant galaxies lie within reach. This window lasts only a small fraction of cosmic time. The age of observability spans perhaps 100 billion years, from when the universe cooled enough for stars to form until expansion carries all evidence beyond horizons. The total lifetime of the universe may extend for trillions of years or more. We live in a brief era of cosmic visibility, sandwiched between early simplicity and later isolation. Future observers will inherit a lonelier cosmos. They will see less, know less, understand less, despite potentially superior technology and intelligence. The universe itself will hide its secrets by accelerating expansion beyond detection range. The loneliness ahead is not a failure of science, but an inevitable consequence of dark energy, and we can do nothing to prevent it. Your cosmic horizon expands by roughly 1 light-year every year. New regions of space become observable as their ancient light completes its journey to Earth. Every second, photons from previously invisible galaxies cross into your cosmic sphere. The particle horizon grows continuously, revealing cosmic territory that was always there, but remained hidden by the finite speed of light. Your observable universe increases in volume with every tick of the clock, but this growth is deceptive. While the particle horizon expands, showing you more of the ancient universe, the event horizon contracts, cutting you off from more of the present universe. These two boundaries move in opposite directions. You see farther into the past as ancient light arrives from greater distances. Simultaneously, you become disconnected from more of the current universe as expansion carries present regions beyond reach. The edge moves differently depending on which edge you measure. Consider what this means for cosmic observation. The farthest galaxy visible today emitted its light over 13 billion years ago, when the universe was less than 5% its current age. You see this galaxy as it was in cosmic infancy, young and full of newly formed stars. But that galaxy has evolved dramatically since then. It now sits over 46 billion light-years away, having been carried by expansion into the distant cosmos. You cannot see its current state. The galaxy's present condition remains hidden beyond your horizon. Every galaxy you observe appears as it was, not as it is. Look at a galaxy 1 billion light-years away, and you see it as it was 1 billion years ago. Look at a galaxy 10 billion light-years away, and you see it as it was 10 billion years ago. The observable universe is not a snapshot of cosmic structure at one moment. It is a backward-looking cone through time, showing different epochs at different distances. The farther you look, the farther back in time you see. This temporal structure creates strange possibilities. A galaxy could have already been destroyed by some catastrophic event, but you continue seeing it because light from before its destruction keeps arriving. The galaxy appears healthy and active in your telescope, but it no longer exists in its current location. You observe ghosts, images of cosmic structures that may have changed dramatically or ceased to exist entirely. Now combine this with the moving event horizon. Some galaxies you can see today will cross the event horizon in the future. Light currently arriving from these galaxies will eventually stop. You will watch them freeze at the boundary, fade from view, and disappear. Meanwhile, other extremely distant galaxies will enter your particle horizon for the first time. Their ancient light will finally complete its journey, revealing cosmic structures never before observable. Your window into the cosmos shifts constantly. The observable universe changes content over time, not just because galaxies evolve, but because different galaxies enter and exit observability. Some ancient galaxies become visible for the first time as their light reaches us. Some more recent galaxies fade beyond the event horizon and vanish. The inventory of observable cosmic structures is dynamic, changing as horizons move. This creates a cosmic traffic pattern. Galaxies enter your observable sphere from the past as their ancient light arrives. They cross through your observational window as you watch their evolution unfold. Eventually, they exit your observable sphere toward the future as they cross the event horizon and fade from view. The observable universe acts like a moving window, showing different parts of the cosmos at different times. The rate of this traffic depends on cosmic expansion. In a decelerating universe, the event horizon would recede, keeping pace with or outrunning the particle horizon. More galaxies would enter observability than exit. The observable universe would grow in content as well as size. But in an accelerating universe, the event horizon contracts. More galaxies exit observability than enter. The observable universe empties over time, despite growing in apparent size. We live during the transition between these regimes. For most of cosmic history, expansion was decelerating as matter's gravity slowed the growth of space. The observable universe steadily accumulated content as more galaxies entered visibility. But about 5 billion years ago, dark energy began dominating over matter. Expansion started accelerating. The event horizon began contracting. We exist during the crossover, when the observable universe reaches maximum content before beginning its long decline. Future observers will inherit a shrinking catalogue of observable galaxies. They will see the particle horizon expand, just as we do, revealing ancient light from increasingly distant regions. But the event horizon will have contracted dramatically, cutting them off from vastly more present cosmic structure. The moving edge will have shifted the observational window to show less variety, less structure, less cosmic richness. The edge moves, and the view changes with it. What you can see today differs from what your ancestors could see, and from what your descendants will see.